Okay, let's get started. Last week we just introduced about Pheloic materials. By the definition, the multiferroics are the materials that possess two or more ferroic properties. For example, if we apply a magnetic field and close it, then the induced magnetization have a remanence. So for this kind of material, we call that would be ferromagnetism. And similar, when we apply an external electric field and return to zero, if there are some reduced electricalization, and this kind of material we call they are ferroelectricity. And when we have we will have a strength as we apply the external pressure and return to zero, then this kind of material we call the ferroelectricity. And today I want to give you a further introduce about the pheloic material is the multiferroics. So if we have if in materials that we have both ferromagnetism and ferroelectricity, this kind of material we call the piezomagneticity. And for the material that contains ferroelectricity and the ferroelectricity, this kind of material we call piezoelectricity. And the most important things I want to tell you is the materials that have magnetoelectricity, which is the compound that contains both ferromagnetism and ferroelectricity. Okay, so a little bit lag. Okay, so shown here is a figure that we have we have already classified three types of multiferroics. Okay, so the x-axis is the electricalization and the y-axis is the magnetization. So these three types is type 1, type 2, and composite. For the type 1 multiferroics, its electricalization is in the range of the 10 to the minus 4 to 10 to the minus 10 to 2. And its magnetization is between the 10 to the minus 4 to almost 1. But for the type 2 multiferroics, it contains narrow ranges. So when we measure this kind of type 2 multiferroics, its electricalization is between 10 to the minus 4 to 10 to the minus 1, and its magnetization is 10 to the minus 4 to 10 to the minus 2. Okay, so the typical type 1 multiferroics is the business iron oxide. And for the type 2 multiferroics, Rmn2O5 is the most important one. But for practical usage, both type 1 and type 2 multiferroics are, I mean the electricalization and magnetization are not good enough. So we artificially make a different kind of multiferroics, which we call the composite. And this composite sometimes it's made by sometimes combine type 1 and type 2 multiferroics. So a proximity effect will make they have a larger in both electricalization and magnetization. Okay, so so before we further introduce this kind of material, and let me demonstrate why does this multiferroic is so important. So in the beginning, I just recalled some basic knowledge that you already learned in general physics. So if we have positive charge and a negative charge, and they have a distance between these two charges, and they will form we call so-called electricalization. So if in a material that we have a lot of, this is electric dipole. Okay, so in compounds, if we have a lot of electric dipole and they align to the same direction, then the sum of this electric dipole called electricalization. So we use the capital P as electricalization. Typically in compounds, there are a lot of I think there are a lot of the compounds that is the ionic crystal. So if you look at more detail, we will find there are positive charge and negative charge. But so they will form a single electric dipole. But typically you would not feel any electricalization in the compound because they are cancelled to each other due to the symmetry. But when you apply an electric field, then you can partially induce the electric dipole. For example, if here is the we apply the positive electric field here and negative electric field here. So the negative charge will tend to go upward and the positive charge will go to downward. So the distance between upper positive and negative charge pair will reduce, and the electric dipole pair here will increase their distance. So we will get net electricalization to downward. Okay, so this is the idea that how to induce the electricalization. Okay, similar, we also have we also have spins, like we talked about in the very early class. So once an atom carries spins, then it will create magnetic moment. Okay, so if we have a lot of the electric dipole moment inside a compound, then the sum of this magnetic dipole moment we call the magnetization. Typically in compounds there are a lot of magnetic dipole moment, but sometimes actually they are always random oriented due to the thermal vibration. But we can also align that with applying external magnetic field. So we may ask one question: can we induce the magnetic ordering? I mean, can we align the magnetic dipole moment by applying DC direct current DC magnetic electric field? The answer is no. Maybe you can create you can magnetize something with AC current, but you cannot induce a compound with this method. Okay, similar, can you induce the electricalization by applying external magnetic field? I mean the DC magnetic field? The answer is also no, because we cannot use the different physical operations to induce another physical phenomena. So sometimes we cannot have both electricalization and the magnetic moment or magnetization at the same time. But there is a very special situation that maybe we can induce this physical phenomena by another operation. So there is an example. If we have the compound that contains positive charge and a negative charge, but for this positive charge, it also carries spins. So in this case, when we apply the electric field, then the ion will move. For example, the negative charge will try to go to the positive electric field side. So and the positive charge will try to go here and reduce the distance from the ion and this plate. But at the same time, these two positive charges will get closer and they will influence to each other. So the spins will try to align to parallel. So we can virtually treat this phenomena like as when we apply an external electric field, then the magnetic moment would increase. So in this case, when we turn on the electric field, then we create electricalization to this direction, but we also induce the magnetization to here. And the electricalization is vertical to the magnetization. So in this case, we may find application for this phenomena. So here is an example. You can check these figures. So in the bottom, let's just take a look at right side figure. Okay, so here is an electrode, and above it is the green color is the multi-pheloic compound, and this blue this blue layer is made by a soft magnet, as we mentioned in the last class, and the that would be pink. The pink layer is a non-magnetic material, but it's a conductor, and the top layer is the hot magnet. Okay, so when we apply an electric field with like this, so it will induce the electricalization downward. And let me remind you that in this case we will also induce the magnetization, but it will point to the right, and this electricalization and magnetization would vertical, okay, perpendicular orientation. So in this situation, when we have a magnetization point to right, then it will also magnetize the above layer to and induce the magnetization also point to right. So if you remember Okay, just wait a moment. Okay, can you hear my voice?
非常的有声音。
Okay. Okay, let me repeat that again. So this is the one unit for magnetic memory. So when we have an electrode here, and the top green layer is made by the multiferroics, and in the center layer, this blue one is made by a soft magnet, and this pink layer is the conductor, but it's magnetic isolated. It's made by a non-magnetic compound. And the top layer is a hot magnet. So when we apply the reverse bias here, then the electric polarization will induce, and to the this direction, I mean they will induce a magnetization point to right, and it will further magnetize the upper layer, and also create magnetization toward to right. So when we measure the resistance between top three layers, we will find one thing. When we inject the current here, then the electron will polarize, and this polarized electron spin will also allow to pass through the bottom layer. So we will go to low resistance state. So in this plot, here is the voltage and this is the resistance. So the reverse bias means we have a negative voltage. So in this case, this is negative voltage. So we go to the low resistance state. But in this case, when we have a forward bias, then the electric polarization is point to up. and the magnetic moment or magnetization is point to left, and it magnetizes this layer to left. Then when we measure the resistance here, we'll go to the high resistance state because the electron spin will polarize to right but blocked by this layer because they are anti-parallel. So in this kind of unit, we are working on the high resistance state, and in this case, we are working on the low resistance state. So that means we can control the voltage to get the signal in low resistance or high resistance state. We may, for example, we can let the low resistance state is equal 0 and the high resistance state is 1. So by operating the voltage and measure the resistance, we can write and read the memories. So this is a very good idea that we can make a 1 unit or 1 bit of magnetic memories. But there is one problem. If for the multiferroics, if you want to operate the electricalization or magnetization, there is a one point is very important. That is, we need to let both magnetic ordering and electricalization or electric ordering working at below the Curie temperature. For example, for bismuth ion oxide, its Curie temperature, I mean the electric ordering temperature, is about 1100 K, and for the its magnetic ordering temperature, near temperature, is about 643 K. That sounds good because mostly we operate this magnetic unit in ambient temperature. But unfortunately, if you have such higher ordering temperature, that means you need to apply a very large voltage when you want to change its state, because the higher ordering temperature means the interaction for this internal electric dipole moment or magnetic dipole moment is very strong. So you need a very high voltage to reorientate its moment. So that means it will use a lot of the electricity inside reading and writing and reading. So typically we want to have its ordering temperature is probably I think a relative of 100 degree above the room temperature, because you can imagine that in your computer case, the temperature would higher to roughly 50 to 80 degree, right? If your memory is close to the CPU unit, I think even that would be higher, about to 90 degree. So to ensure the memory will vaporize, you need to have a little bit higher than the ambient temperature, but you don't want to have too high ordering temperature. To avoid, we need a lot of electricity for read and write. And another issue is this is for the type 1 multiferroics. For type 2 multiferroics, its ordering temperature is too low. That means even at the room temperature, it cannot hold magnetic or electric ordering. So it's always in a random state. So it is also not applicable. So there is one issue is how to find out a material that have suitable working temperature. This is the first issue. The other issue is if you want to make a magnetic memory, the recording density is quite important. You don't want to make you don't want to use a very large unit to do recording, because the density for the typical hard drive is roughly about the 600 gigabit per inch square. So if you do not have such kind recording density compared to the typical hard drive, that may not have any commercial value for application. But unfortunately, for most magnetic material, it has limited working size. This is because the ferromagnetic. Let me show you here. Okay. So for the typical magnetic material, ferromagnetic material, its magnetization is proportional to, if you remember that, we have an equation right like this way. Okay, so the B is an external magnetic field you may apply it, and the lambda M is the internal magnetic field that's induced by your own magnetization. So this magnetization is the same as this one, but here is a proportional constant. So that means if you reduce the size, for example, this is ferromagnetic material. If in this case we have, for example, we have 3 mu b, and when we reduce the size here, this is only 1 mu b. So that means the internal magnetic field will 3 times less than the original one. And in this case, if the thermal energy typically we will write a kBT. If the thermal energy compared to your internal magnetic energy, sorry, mu h, sorry, mu h. I should write a mu b, and this mu is same as this magnetization. So when you reduce the size here, then you also reduce the mu, and it would not resist the thermal vibration. So we may not order it at specified temperature. So this is a very important issue for make a magnetic material. Its size will particle size will correlate to its ordering temperature. So you may think that maybe we can make a very tiny BFO and reduce its ordering temperature. Then we can also make a very good unit. So this is the way that the industry do. But if you want to further increase the recording density, and then its ordering temperature will below the 300 K, that means they have a size limited. So the second issue is the minimum functional size will be very important. So in this study, I want to introduce the discovery of the type 2, not the type 1, the type 2 multi-Pheloics. And in this case, the ordering temperature and the minimum function size are very important. We want to increase its ordering temperature, but we also want to reduce its functional size. So let me introduce this study to you. So for the Rmn205, the type 2 multiferrox, it is made construct in combining ultrahedron and the pyramids. So the MnO6 ultrahedron is made by tetravalent magnets, and the pyramid is made by the trivalent magnets. So when we have a top view from the C-axis, it will be look like this. This is the ultrahedron and this is the pyramid. And when we have a top view from the A-axis, we will find the ultrahedron is aligned here, and the pyramid is in between two ultrahedron line. So its structure would be look like this. The yellow arrow is the spin of the magnets. So you will find there is no any straight line. They would be look like a zigzag chain between each magnetic dipole moment. So how does this Rmn205 become multiferrox? Typically, if we have a MnO chain, that means in this case the brown circle represents the trivalent magnets, and the green circles means the tetravalent magnets, and in between them there is O divalent -2 action in between them. So typically, when we check this block, we will have electricalization from Mn3 plus to Mn4 plus. But here we also have another electricalization from Mn3 plus to 4 plus. So they will cancel to each other and get zero electricalization. But if you remember the structure that in the previous slide, we know each chain would be look like zigzagly. So in this case, if we further reduce the temperature, the bond between magnets will shrink, and the magnetic moment will affect to each other, so they will align parallel. So in this case, we induce both electricalization in this unit and this unit, and maybe here is a unit, and we also induce the magnetization. So this structure we call the frustrated magnet. That means you need to shrink its bond length and induce the both electric and the magnetic ordering. So this is the case. So the zigzag chain look like this zigzag chain. Okay. So in this sample, there is a very complicated electricalization and magnetization against two temperature. I don't want to talk too much detail about it, but the very important thing is, once the electricalization induced, then the magnetization also appears at the same temperature. That's very different from the type 1 multiferric. For the BFO, the electric ordering temperature is far away to the magnetic ordering temperature. But for type 2 multiferrics, they are happen at the same temperature, almost the same temperature, because they are correlate to each other due to the structure. So that's why we want to study the type 2 multiferric, because this is the ideal compound to make magnetic memory. Okay, so how to make this kind of multiferric nanoparticles? So we have a chemical formula here, and we can mix them and seal it into the stainless steel can and use the hydrothermal method to make it. After we got the result powder here, we can use this powder to heat up to a certain temperature to increase its size. So we can get various size of the nanoparticle multiferroics. So why we need to study the nanoparticle multiferroics? Because we reduce its size, right? Remember, the issue too is we need to know the minimal functional size. So when we got this kind of nanoparticle multiferroics, we firstly we need to check its chemical formula is still hold Rmn2O5. So we do the X-ray diffraction analysis. So we found here we make a 6 sample near at a different temperature. It's 240 degrees Celsius, 300, 500, 700, 900, and 1100 degrees Celsius. So ideally, we may have 5 different sizes nanoparticle, and in this study we found these 6 samples are all in the correct chemical composition. And we also need to check its detailed structure. So we use the high resolution TM to check its atom is formed as a correct location. So this is the TM image. We found one thing, that is for the hydrothermal method, we will make a nanoparticle looks like a rice grain, and it has specified directions. We found no matter how you near the sample, the longer directions always at the C-axis of the crystal, but along the another short side, they are not specified crystal planes. So here we will use the C-axis. We will name the LC to represent its size. So how do I know its growth along the C-axis? Because we use the solution area electron deflection (SAED) to determine its crystal orientation. So you will find all kinds of the multiferric so-called rice grain is always at the it always grows along the C-axis. So we may say this is the long side is the actual direction, and the short side we will show the radial direction. You can think that would be like a cylinder. Okay, so we can make a statistic to check particle size, because there are a lot of the multiferric nanoparticle inside one TM image. So we need to make some statistic. So the actual length means the longer side, and the radial length means the shorter side. For the 240 degrees Celsius sample, we found its actual length is 58 nanometer, and the radial length is about 23 nanometer. So we can do the similar thing to all kinds of sample. We found at a different temperature, they will have different actual length and the radial length. And one more thing, the anneal did have an effect to the particle size. You will see the number, no matter in actual length and radial length, will increase. So that means we already got different sizes of multiferroic nanoparticle. So we use the actual length I mean the longer length as its particle size, we use the average LC as its notation. So this is a near temperature against the radial length and actual length. But for more accurately, we fit it with the 2D Gaussian. So we also got another number here. So this is the fitted radial length and the fitted actual length. So this is the result for the 2D Gaussian fit. And this is the distribution of the obtained particles. So we will name the, for example, we don't use the TA equal to 240 degrees Celsius sample. We use the LC is equal to the 25. LC is equal to 58 as the sample name. So we got this size from the HRTM, but there is a one problem. That is, how do you know the near effect did increase its size? Sometimes the particle will stick together, so you need to check the size is real growth or they just stick together. So how to check that? You can use the X-ray diffractions. You must to check its peak. It is just only contains one Miller index. So that means there is no two peak combined together. Okay. So for a single peak, when you found the half width become wider and wider, that means the particle size is become smaller. So the wider half width means the smaller particle size. So in this case, we can calculate its corresponding particle size. But the difference between the X-ray result and the TM result is the X-ray is just only considered about the older length. What does that mean? So for X-ray, this is the crystal plane, and if inside a particle there are crystal plane in this size, and there's another different crystal plane in this size, then you will find one thing. The TM result will give you this size in this. This would be seen in TM, but the X-ray would detect the size like this. Okay, so sometimes you will find the X-ray, the size determined by X-ray will relatively smaller than the TM1. So in this case, we found, shown here is the comparison between the X-ray and the TM. So you found that the actual length and the radial length is labeled by the solid square. So that would be this one, and the black solid circle. So that would be this one. Okay. So we can also calculate the crystal size by using the X-ray diffraction half width. So we can check the peak width along the H00, which means along the A-axis, and the 0K0, which means along the B-axis, and the 00L, which means in the C-axis. So we found the blue and the orange solid square. They are very close to the result obtained from the TM. But along the C-axis, the green solid square is a little bit less than the TM result. but it's still in the error bar. So what does that mean? That means along the c-axis, although it looks longer than the size along A and the B axis, but actually it would be combined by many particles. And when we times 3 along the c-axis, we found this result will very close. This result got from the X-ray will very close to the TM. So that means the TM image is actually look like this. We got the TM image like this one, but actually inside the particle they are combined by 3 particles. Okay, so this is the very important when you want to make the real devices. Actually, that would be combined by this one. And we also discover this. We need to know its magnetic property. So here is the chi-T curve. Chi means the magnetic susceptibility, which is defined as here. The chi is defined the magnetization variated with external applied magnetic field. Okay, so you can say it's the response to the magnetic field. So we can fit that with a Curie-Weiss law to get the ordering temperature, or we can use this equation to get its interaction inside the compound. So the E1 means the spin interaction, and the E2 means spin orbital interaction. That would be like this one. So this is the nuclear core, and this is the orbital of the for one electrons. So electron has spins, and it also has orbital moment. Okay, so the spin and other spin will have some interaction, but the spin will also have some interaction to orbital. So we can fit these equations to obtain the spin-spin and the spin-orbital interaction. Shown here is the table of the result. You don't need to remember that. There's just 2 things you need. I can tell you. That is, we fit the spin-spin interaction is about 200K to 150K, and the spin-orbital interaction is very low. It's probably close to the 20K to 60K. So that means we can almost ignore spin-orbital interactions, and the most important is spin-to-spin interaction. That means the we need to take care about the atom to atom magnetic ion interaction. Okay, so we need to answer the question that we set in the beginning. Is the size affect the magnetic ordering? The answer is yes. In this case, we found the magnetic ordering is here, and this is the smallest size of the multiferric nanoparticle, and this one is the larger size. So we found the magnetic ordering is decreased with the size, so it would be looking like this. So unfortunately, we do not improve the magnetic ordering here, and even worse. Okay, we just ignore this one. The other thing is cohesivity. Okay, let me finish this part and then take a break. Okay, so you can find that for the smaller size, we also have smaller cohesivity here. So this is 0.028 Tesla, and it will increase with size until to 0.057 Tesla. Okay, that would be quite small. compared to those hard magnets. But we at least we know its cohesivity is property proportional to its domain size. Okay, so in here we know the LC means the actual length, means the longest length of the nanoparticle or nanorod. It will increase with increasing anneal temperature. So anneal effect will increase the size. And the TN tell us the spin orbital interaction is very important when we when the ambient temperature is above the TN. And the crystal and the magnetic domain are increased with increasing anneal temperature. And the size of magnetic domain are proportional to crystal domain. The one more important thing is the magnetic ordering temperature is increased with size, but unfortunately they are still at a very low temperature, below the 30 K. So in this case, this multiferroic would not in the practical application. So actually, we also try to looking for different kind of elements to check if we can improve the ordering temperature and the critical length, the critical size. So we try to substitute its rare earth ion. R means rare earth. So remember that this compound is Rmn2O5. So we found there seems to have some rule. That is, if we have a larger size, then it will have larger critical length. So here are 3 samples that we are not yet tested, and there are another 5 samples we are not yet tested. So what does this mean? If we want to look in for, it seems to tell us that if we want to look in for Rmn2O5 type 2 multiferric without any critical length, that means even you have a very small tiny size, it will still hold magnetic ordering. That would be very ideal for making magnetic memory. So we need to go to the high atomic number element, such as the holmium, erbium, to ruthenium, something like that. You don't want to looking for the low atomic number elements such as the lanthanum, cesium, and praseodymium. Okay, at least this is give us an idea where to looking for good type 2 multiferroic. Okay, so it's 10:05. So let's take break for 10 minutes. So we will return at the 9:45. Just take a break.